This is the lecture for Friday, March 27th. We will continue our discussion of quantum chromodynamics. We already introduced the quantum chromodynamics Lagrangian. It was a bit complicated. We worked very hard to explain all the various terms in this Lagrangian, like the quark field, psi, and its Hermitian conjugate psi bar, and the gluon field G mu alpha here. And then we also had these objects like the field strength, the field tensor, G mu nu. All right, and there was a complication to this G mu nu term here, that for the gluons, not only did we have things with derivatives, but we had things that were quadratic in G. And so if you put this back into here, you see that you end up getting terms that are not just quadratic in G in the whole term here, but you get cubic terms, 3 powers of G, as well as 4 powers of G. And so as a result, the Feynman rules that you get for quantum chromodynamics is a bit more complicated than what you got in quantum electrodynamics. So in addition to having simple diagrams like you had for quantum electrodynamics, like this, where you have a quark interacting with a gluon, and where we had a gluon propagator and a quark propagator. Okay, so remember, this is for the quark, this is for the gluon, and this is the vertex between the quark and the gluon. But because of this term here having these cubic and quartic terms in the gluon field, we end up getting these functions, these vertices like this, where the gluon self interacts, 3 gluon legs come out, or 4 gluon legs come out. Okay? And this turns out to change the character of quantum electrodynamics compared to, quantum chromodynamics compared to quantum electrodynamics. We'll come back to exactly what is the difference in a moment, but let's just talk about the quarks themselves. So we have 6 types of quarks, 3 generations, and so here are the quark masses. The up quark has a mass of about 3 mega electron volts, okay, and the down quark mass has a mass of about 5 mega electron volts. Sometimes it's convenient to calculate quantities like the average of the two, as well as the ratio of the up and down quark masses. It turns out there are some observables like meson masses and such that are sensitive to this ratio. Now the strange quark mass is about 100 MeV, and the bottom quark the Chomp quark mass is about 1,200 MeV, or 1.2 GeV, and the bottom quark mass is about 4.2 GeV, or 4,200 MeV. Now the top quark mass is much bigger than all the other quarks in mass, and it's about 172 gigaelectron volts. So this is actually bigger than the mass of the W or Z boson. So as a result, the top quark can actually spontaneously decay. You can go from a top quark to a bottom quark, and you can spit off a W plus particle as a result, and so it's actually unstable to weak decay. This sort of process is not possible for the other quarks because the other quarks have a mass less than the W boson. Now, let me talk a little bit about the diagrams that we get coming out from the Feynman rules. So we already discussed this, but vacuum polarization, remember we were talking about the interaction of 2 electrons, and there was this vacuum polarization diagram. So the wavy lines are for the photons, and the curly lines here, so perhaps you can't see the difference. This is what I mean by a wavy line, whereas this is a curly line. This is for the photon, and this is for the gluon. Okay, so we already talked about this vacuum polarization diagram for the for the quantum electrodynamics for the electron. But we can also have a diagram like this for quarks involving the gluon. Okay, and this is also called a vacuum polarization diagram. However, in the case of the gluon, we can also have a loop that involves gluons. So there's also this diagram. And this diagram has a very different character to it. In some sense, it has an opposite sign to it than compared to the quark loop diagram. Okay, and this actually ends up making all the difference in the world. When we talked about the screening of charges, so if I have a plus charge here for quantum electrodynamics, remember we talked about having little dipoles that screen the charge and make it look weaker at long distances. Well, it turns out that this loop here, which has the opposite effect as what you get with the quark loop, you actually get anti-screening. And the reason this happens, if you want, is because the gluons themselves have color, and it actually ends up amplifying the strength of the color charge. And so instead of screening, you actually get what's called anti-screening. The color builds up as you get further away. And so if you have a quark and an antiquark, let's say, and you try to pull them apart, you find that the potential energy versus separation D, and you try to measure the potential energy, it just keeps growing up to infinity. Okay? And so this is what's called quark confinement, the confinement of quarks. So now, that means we cannot actually see individual quarks. So then you might ask, what the heck was I talking about when I said quark masses? How do you see quark masses? Well, it turns out we can't see quark masses directly, but only indirectly. And we have to do experiments in a very clever way, where we try to make the quarks so that they behave like free particles, which they're not. But it turns out that at high energies, these quarks do behave almost like free particles, and that's how we can, from high energy scattering experiments, collisions, we can actually infer the quark mass it's actually a very clean measurement, but it's very indirect. Now, how do we do all this? Well, it all relies on the fact that the interactions get weak at high energies. Okay. So Q squared, that's, if you do a scattering experiment, the amount of momentum you transfer, let's say you have two particles scattering each other, sort of like this diagram here, I have the two electrons scattering with each other. The amount of momentum, that's what we'll call Q mu if you want, for the 4 vector. And so Q squared then is just the 4 momentum squared of the momentum transfer. Okay? So the higher Q squared is, the higher the momentum that you're transferring through. Now, if you calculate how strong is the coupling, the quantum chromodynamics coupling, okay, alpha S is g squared over 4 pi, it turns out that as you increase the coupling, increase the energy, you decrease the coupling. And it has this functional form to it. It turns out to be 12 pi over 22 minus 2 times the number of flavors, which is the number of quark flavors, which is 6, for the up, and then we have up, down, strange, charm, bottom, and top, 6 quark flavors. So 22 minus 2 times 6 is 10, so there's a factor 10 here, times the logarithm of Q squared, that's the momentum, 4 momentum transfer squared, over a fundamental scale that's called lambda QCD squared, which has a value of about 200 MeV, mega electron volts. Okay, so this coupling gets weaker as Q gets larger, but rather slowly as a logarithmic function of Q. So we have this sort of dual picture where we have at high energies, or short distances in quantum mechanics, high energies is the same as going to probing shorter distances. You would have asymptotic freedom, that the particles behave like that they're not interacting. But at large distances, the interquark coupling becomes very, very large, and you have confinement. So that's sort of the dual picture. You have confinement at large distances, asymptotic freedom at short distances. And so this calculation of this behavior is what's called this is what's called asymptotic freedom. The fact that as q squared goes to infinity, alpha s of q goes to 0, this property of asymptotic freedom. This calculation was first done by two groups. So one was at Princeton, David Gross and his graduate student Frank Wilczek, and the other group was in Harvard. Sidney Coleman had a graduate student, Henry David Pulitzer, who did this work, and these three people won the Nobel Prize in 2004. So here is confirmation of this behavior, that we have this running strong coupling constant that can be seen from various experimental data. For example, deep inelastic scattering. That's when you have an object like a proton and you bang it with a collision of, for example, an electron, and you look at all the stuff that comes out, because you pump it with enough energy that it can produce almost anything. So that term inelastic means you look for you destroy the original state and you just look for other things that come out. You can also have E plus E minus annihilation, where you have an electron and positron. They annihilate each other, form a virtual photon, and then you look for everything that comes out of that. You can do more complicated collisions involving protons, proton-proton or proton-antiproton. You can also look at heavy quarkonia. That's when you have things like a bottom quark and an antibottom quark. They form a balance state, and you can try to measure the potential between the bottom and the antibottom quark, and that can give you a reading of the running coupling constant. So anyways, putting all this experimental data together, you find that it's fitting quite well with this theoretical curve, what you expect to get with that 1/log q squared behavior, and it works quite well. Now, it's customary to actually quote this running coupling at the value of 91 GeV energy, right around here. That's because that's the mass of the Z boson, so there is a resonant enhancement right at that peak, because you form a virtual Z boson at that point, and so you see a big spike in the data, and so that's a good calibration point. You know exactly when you're sitting on the Z boson, because your cross section goes way up, and so that's a good calibration point to quote alpha s at that point. Now, so as a function of increasing energy, the running coupling for quantum chromodynamics decreases, but in QED it goes in the opposite direction. So if you know in QED at low energies, you have 1/137 for alpha for electricity magnetism. Then at the scale of about 90 GeV, alpha is bigger in the case of quantum electrodynamics, but not that much bigger. It's about 1/127. So let's talk a little bit more about these quarks and these light quarks in particular. Okay, so we talked about these quark masses, and so one thing you'll notice is that the masses of the up and the down quarks are quite a bit smaller than the masses of the other quarks, as well as this pretty much any other mass scale in the quantum chromodynamics Lagrangian. So this is about 3 MeV, and this is about 5 MeV, and that is quite a bit smaller than 100 MeV. Right? We said at 1,200 MeV here, things like that. And so one can consider this approximation in which the up and down quark masses are 0. And that's actually an interesting question to ponder. So let's talk a little bit about chiral symmetry. So we've talked about helicity. So helicity is the component of spin in the direction of the momentum of a particle. So let's say a particle is moving in the direction of that my pen is pointing to the right like this, okay? And let's say it's spinning like this, then this was what we call a right helicity particle, right-handed, okay, helicity. Now, if it's spinning this way, then it's what's we call a left-handed helicity. Now, if I were to go faster than this particle itself, then it looked like the momentum is going in the opposite direction. So what was a right-handed helicity particle, because to an observer that's moving faster than this particle, then it will look like a whole left-handed helicity particle because the momentum is pointing in this direction. Okay. So now, if you so the fact that you can catch up to a particle and flip its helicity, that's related to the fact that the term in the Lagrangian that involves the mass of the particle, that is the term that couples the right-handed helicity to the left-handed helicity, right with left, left with right. So you annihilate a right-handed particle, create a left-handed particle. Annihilate a left-handed particle, create a right-handed particle. It turns out that all of the other terms in the quantum chromodynamics Lagrangian, the other terms here, these guys here, okay, these do not couple left with right. They're only left with left and right with right. And so, in the limit that the quark masses can be neglected, like the up and down quark masses are really small. If you allow them to be exactly zero, we actually have an extra symmetry, which is called a chiral symmetry. What is this chiral symmetry? It's basically saying that I can treat the left and the right helicities of the quarks as being independent of each other. So I can do things like I can take the left helicity of the up quark and the down and the left helicity of the down quark and do a rotation. I can interchange the two while not touching the right-handed helicities, or I can maybe interchange the right-handed up and down quarks. Okay, and that would be another transformation on the right-handed quarks. This is what's called chiral symmetry. The word chiral has to do with handedness. Okay, and so this is actually an approximate symmetry of the quantum chromodynamics Lagrangian in the limit that the light quark masses go to zero. Now, it turns out that this chiral symmetry, though, is spontaneously broken. Now, we talked about spontaneous breaking of symmetry before when we talked about the Higgs boson. So I remember we talked about there's this field phi that has some sort of fields of potential that looks something like this, okay? And the symmetrical point phi equals to zero is disfavored because it lives at the top of the potential, and you want to fall down to the bottom of the potential, but in order to fall down to the bottom of the potential, you have to pick some direction. It gets some non-zero value for the for its average value. Okay, the same thing happens here. There's this spontaneous breaking of this symmetry and this chiral symmetry, and it turns out that the expectation value, the vacuum expectation value of this operator, that is the thing that would come from this. This is supposed to look very similar here. Okay, this is the type of term you get for a quark mass term. It actually becomes non-zero, and this is a signal that the chiral symmetry is spontaneously broken. And we'll talk more about this later when we talk about pions. It turns out that the pions become massless as a result of this effect. But let me just finish off this lecture by talking about the QCD vacuum, because this is a very interesting story. Because of this complexity of the diagrams you can get, you not only have this vacuum polarization involving the quarks, you can get the vacuum polarization involving the gluons. The gluons can interact with themselves. It's a very strongly coupled problem, so you can get arbitrarily complicated diagrams. And so how in the world would you calculate such a thing? Well, the only controlled way to calculate this, to try to figure out what the vacuum's structure actually looks like, the quantum chromodynamic vacuum, you have to do a calculation, a technique called lattice quantum chromodynamics, lattice QCD. So you have to put these things on the supercomputer in the following way. So first of all, I should tell you exactly how people do calculations in quantum mechanics or quantum field theory. Right? When we write down a Lagrangian, there's a formulation of quantum mechanics called a path integral. So I won't have a lot of time to discuss this, but you have some Lagrangian, okay, and so we've been talking about the Lagrangian for quantum chromodynamics, and what we want to do is, instead of just trying to find the extremal or maximum or minimum configurations for this Lagrangian, in quantum mechanics, we actually want to do something a little bit more complicated. We actually want to figure out the integral over all possible configurations for the quark and the gluon fields of the exponential of the integral of the Lagrangian over all of space and time. Okay, I know that sounds really complicated, and it is actually. Okay, you have to do an integral over these gluon fields as well as an integral over the quark fields, like this. Okay, this is what's called a path integral path integration. Okay. Don't worry, I'm not going to go into details of this. This is well beyond the scope of this class, but that's exactly what needs to be done to do these calculations. And what lattice quantum chromodynamics does is it does exactly this calculation using Monte Carlo simulations. Remember, we talked about Monte Carlo simulations using random numbers. And what they're doing is they're sampling the gluon fields and the psi fields and for the quark fields, the gluon and the quark fields, and they're calculating this integral for all possible random configurations. And in that way, you can actually produce a simulation of the quantum chromodynamics vacuum. And when you do that, you can then get these pictures of what the supercomputer does, and this is a nice illustration by Derek Limeweber at Adelaide, where he's showing then just the local energy densities, field strength configurations for the gluon fields in these lattice quantum chromodynamics simulations. If you want to see the animations of this, you can check out the link here on the lecture notes. Okay. So, by the way, the size of the box is about 2.4 by 2.4 by 3.6 femtometers wide, which is big enough to hold a couple of photons. So I will stop here, and hope you guys have a good weekend, and I'll see you on Monday.